Hello. So this is the third video segment of Lecture 7, Part 2. So what we're going to do is show you how to solve for the model dynamics in a little more convenient manner than what we were doing with the equations and levels. If you remember at the end of the last video segment, we had a complete list of the equations of the model. We started off with output being determined by how much capital and effective labor there is, the product of Z and L, with the Cobb-Douglas production function. We used the fact that firms pay workers their marginal product of labor to get that the labor compensation is a constant fraction of this level of GDP, with a constant fraction being this labor share parameter. The remainder of GDP is retained, is available to owners of firms as gross operating surplus. And we assumed that owners of firms pay out a constant fraction of that gross operating surplus, so 1 minus S times alpha times GDP, as dividends, and they invest the rest, so that's S times alpha times GDP. They invest that back in their business. And when we say they invest it, what they're doing is purchasing physical capital that they're leaving in their business. They're using tomorrow in their business. So we have the physical capital stock today with some depreciation. That level of investment gives us the capital stock tomorrow. We have GDP. A constant fraction of that is consumed. Why? Because workers consume their wages and their dividends, and when you add up these two fractions, that's how much consumption is. And we calculated what the return on capital would be. It's tomorrow's return on capital will be tomorrow's gross operating surplus, net of depreciation, so that's the net operating surplus, divided by the capital stock. And we can work out from these formulas that this is the equation for what that return on capital is. It involves the capital share parameter alpha and the capital to effective labor ratio and the depreciation rate. And we mentioned at the end of last class that if you give me all the parameters, which includes the capital share parameter, the depreciation rate, the corporate saving rate, a path for how many people there are in the economy, that's determined by population growth, a path for technical change over time, and an initial capital stock, I can just use these equations over and over again, always getting a new capital stock and then using the new labor force and the new Z to just go through and give you a whole path for all of these variables over time. But when we solve this model, because we're going to allow for growth in population and technology over time, it's going to make sense for us to solve the model in terms of a little k, which will denote the ratio of physical capital to effective labor. So we're going to restate the model equations using this ratio because that is going to make solving the model easier and have it converge to a steady state as opposed to something that's growing over time. So this is a presentation of the restated equations of the model. You notice now that output is the capital to effective labor ratio, little k, which is big K over Z times big L, all raised to the power alpha, and but then multiplied by Z times L linearly. So you can convince yourself, if you look at this equation here, and you look at this equation, given the definition of little k, that this equation is equivalent to the previous one. Otherwise, all these equations stay the same. These ones about how much wages are, dividends, gross operating surplus, investment, consumption. But we now have to restate how the capital stock evolves, because we're doing things now not in terms of big K, which is the absolute amount of capital in the economy, but in terms of the capital to effective labor ratio. And what I've done here is I've already substituted in for what investment is. This is investment, but I've already substituted in that investment is this fraction of GDP, S alpha GDP, and the GDP is given by this. And since this equation is the capital transition equation divided by the amount of effective labor, I get this expression. And this here, the reason we have this term here is this is the absolute amount of physical capital at time t plus 1 divided by effective labor at time t plus 1. So to have a consistent division by effective labor at time t across this entire equation, we have to multiply by the ratio of effective labor at time t plus 1 to effective labor at time t, and that's just given by this expression. Because you remember that these growth rates are defined in terms of the growth rates of labor and technology. Okay, and our equation for the return on capital was originally written this way. You notice that we solved for it. We can just plug right in here. The return on capital is going to be, oh, no, it's here, just the ratio of capital to effective labor raised to this power. And so we have the same set of parameters we had before, except instead of saying we have a sequence of L and a sequence of Z, we have a sequence of growth rates of L and a sequence of growth rates of Z and initial conditions for Z and L and an initial value of capital relative to Z0 times L0 to effective labor at time 0. So this is just a restatement of the model equations that we had before. Now, when you look at these model dynamics, in general, and we'll do this in Excel, once I pick these three parameters and these initial conditions, I can take any path of growth rates and just go through these equations in Excel, and I've posted Excel sheets that do that we'll discuss in a little bit, that just crank out the answer for what happens to GDP, wages, dividends, consumption, investment, the capital stock, and the return on capital. So we can do that. But one thing of special interest will be what we call a balanced growth path. What happens when the growth rate of technology and labor is actually constant? So when it's constant, this capital transition equation, these are now constants right here. So we're writing it this way with those constant things being constant. And if you look at this equation, we actually don't have to use any other equations of the model. We've already substituted out that investment is a constant fraction of output per effective worker, or investment per effective worker is a constant fraction of output per effective worker. So that's where this is coming from. This is the corporate savings rate, and this is the fraction of output that is gross operating surplus. And you could notice something about this equation is that if we make a plot of it, there's one steady state of this equation where all these little k's are 0. Because if I stick a 0 in here, and in here, and in here, then all of these things are, these two sides are equal. But we're going to ignore that one. That's an economy where it's impossible to produce anything because you don't have any capital. But there's also a positive steady state. There's a K bar, or ratio of capital to effective labor. We're going to show that this economy converges to that ratio. That is a K bar that is a solution. What's a constant value of K that I can stick in on both sides? This is that solution that is the steady state, that if you start with that capital to effective labor ratio, you'll end with that capital to effective labor ratio. And we can see that the steady state ratio of capital to effective labor is depends on what the corporate savings rate is, what the capital share is, what the growth rate of technology is, what the growth rate of labor is, and what the depreciation rate is. And of course, the alpha enters again in here. Now, on this balanced growth path, a couple of things are true. If we think back to the stylized facts that we have a constant ratio of capital to effective labor, so that's true. We have the GDP on the balanced growth path is then given by that constant ratio to the alpha times the amount of effective labor. So GDP grows at a constant rate, which is the growth rate of effective labor. And output per worker, or output per capita, which is something we looked at, grows at a constant rate, the growth rate of technology. So remember, we said a stylized fact was that for a long time, output per person in the United States grew at a constant rate. Well, we would model that by being on a balanced growth path with a constant growth rate of technology. Some other facts that are true on a balanced growth path is that this is actually always true. The share of labor in output is constant. So we talked about the share of labor. And something else that is true, remember we talked about the return on capital being roughly constant for about 40 years. Well, the return on capital is just given by this formula. And if depreciation and the capital share is constant, we're on the balanced growth path, then this implies that the return on capital is also constant. So a lot of times when we think about what's going on over the long term in the US economy, we end up thinking of it in terms of being on a balanced growth path of a Solow growth model. And we'll discuss how to pick parameters to mimic key features of the US economy. I'll mention as an aside that I've shown you that some of these basic facts, like the labor share being constant, or concerns about is the real interest rate changing over time, these types of concerns raise questions about, are we still on a balanced growth path? Is there some change of parameters? What's going on? There's a lot of active research about this. But what we're going to do for the rest of Lecture 7 is to actually use the model just with a simple Excel sheet. I've actually posted 2 Excel sheets that have, the spreadsheets that have the numbers of the calculations that I'm about to go through that you can look at. Those are on the class website. But we're going to go through some calculations of how you might use this model and what its implications are. And so I'll start that with the next segment of this lecture.